Hello, I'm Umnik. Today I will be solving the first round for second division, and I will explain what I'm doing along the way. Half an hour after the end, I will stream virtual participation in the previous second division round on Twitch. Okay, in problem A, we are given an array of non-negative integers. We can do at most k operations. In one operation, we can choose two elements, add one to the first element and subtract one from the second element. So basically, we're taking one from one part of an element and move it from one element to the other. We want to make the array lexicographically minimal using most key operations. When we want to make something lexicographically minimal, we first want to minimize the first element, then the second, then the third, and so on. Obviously, the sum of all the elements will remain the same. So the optimal solution is to go left to right and try to decrease each element by moving its parts somewhere else. And where should we move it? Well, we will increase some other element. We don't want to increase elements that are closer to the beginning, so we will always increase the last element. And we can't then decrease last element even if we have some operations. Because there is nowhere to move its parts. Like, we can move them to the left, but that's worse for us. We'll go left to right. We don't want to look at the last element because it doesn't help. So here we can't make the elements negative, so the maximum number of operations we can make on this particular element is minimum of the element itself and k, which is the number of operations we can do. So we want to make x operations. Each one decreases this element and increases the last one. And we have spent x operations, so we will decrease k by x. We should have at most k operations, right? Not exactly k. in problem B, we're given an array. We can take two consecutive elements and replace them by their XOR. We want to make an array with all the elements equal, but there should be at least two elements remaining. So first thing we can notice is that basically we are splitting the array into segments and then taking XOR on each segment. So after some operations, each element is just XOR of some segment of elements of initial array, and this element segments should be non-overlapping and they should cover all the array, so in order. So basically we are asked if we can choose such segments. Right, then we can calculate prefix source and so if we calculate prefix source, then XOR on segment is XOR on this prefix, like kind of minus XOR on this prefix, but minus is like the operation which is inverse to XOR, which is just XOR itself. So the XOR on this segment is just XOR of prefix XORs into endpoints. When we want to split the array into segments, we're basically choosing what will be the split points, and we have the split point in the beginning and in the end for sure. We have to choose at least one split point after that, and let's look at the sequence of prefix source in the split points. We know that this is 0 here, because in the beginning the prefix source is 0. Then we will have something here. Then the XOR on this segment is X. The XORs on each segment should be the same, so the XOR on each segment between two split points should be X. So the next prefix XOR is 0, then X, then 0. So it should be alternating, and well, we can't choose the XOR in the end. So there are two situations. If the XOR is in the end is 0, then basically we can choose any split point and we will be good. It will be 0, X, 0, even if X is also 0, it's all fine. And if it's not 0 here, then well, it should be X, obviously. And we want to find a subsequence of form 0x, 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 basically. But it doesn't make sense to have it greater than 0x, 0x. Like more repetitions, because, well, if we have this subsequence, then we also have this subsequence. So we will just calculate prefix XORs. Look at the last one. If it's 0, then the answer is just yes. If n is at least 2, and yeah, n is at least 2. And if it's non-zero, then we want to check if there is such subsequence, which is done greedily. So the solution is linear. The limitations are smaller, and I think that's because we can also like notice this idea without like that we only have to have only 3 or 4 prefix sums without actually looking at the prefix sums. Let's say that we have achieved what we wanted and left at least 4 elements, then we can have 3 consecutive elements, take source of them, and it also will be fine. So if there is a solution with either 2 or 3 elements, and we could just for 2 we could just try all the positions where we will make the split, and for 3 also try pairs of positions where we can make the split. After that we have to somehow take the XOR in constant time, which is done by prefixers, so I don't really see well, it's a bit easier, but they really, if you can make this quadratic solution, then you also should be able to make linear one. We won't even store the initial array, we will only store the prefix source. If the last one is 0, then the answer is just yes. Otherwise, we want to find subsequence 0, the last prefix sum, 0, the last prefix sum. If the next element is what we want, then just move the pointer. We have found one more element of the sequence. And if we have found all of them, then the answer is yes. Otherwise, it's no. In problem C, we are given an array which is not very long, and the elements are also kind of small. The array is good if we can't split it into 2 subsequences with equal sums. We want to remove the minimum number of elements of the given array such that it will be good afterwards. Okay, so it's obvious that the array with odd sum is good, because if we will split it into 2 subsequences, sums of both subsequences should be integers, and if they're equal, then the sum of the whole array was even. So if we can get our array to have odd sum, it will be great. if there if the sum of our array is odd in the beginning, then the answer is just 0. And well, we should actually check if the array is good in the beginning. If it is, then the answer is 0, and it is done by a simple knapsack. That's why the elements are small. Otherwise, we have to remove something, and well, I state that we can remove one element always. And the idea is to kind of make the sum odd. If we have at least one odd element, then we can just remove it. Otherwise, all the elements are divisible by 2. Let's divide them by 2. It doesn't change anything. And repeat. After some repetitions, we will find the odd element. Well, basically, we want to find the element with smallest power of 2, which divides it. And that's it. So first, check if the array is good in initially. For that, we want to try and split it into 2 subsequences with equal sums. So we want to find, is there a subsequence with sum which is equal to half of the sum of the initial array. The sum of the initial array is at most 200,000, so we can do knapsack in n squared times the limitation on elements. We can also optimize it with bit sets, but it is not needed in this problem. And after that, just find the element with smallest power of 2 dividing it, and that's it. Let's write it with bit sets because it's just easier that way. Let's calculate the sum. If the sum is odd, then the answer is 0. Otherwise, let's calculate knapsack. If we can't make half of s as the sum of the subsequence, then the answer is 0 again. Otherwise, let's loop our elements, and for each element find the power of 2 which divides it. And we can't delete 0 elements, but we can delete 1, so that's Okay, in problem D, for an array, we want to calculate the minimum number of segments we should split it into such that the least common multiple on this array is equal to the product on this segment. And then we should answer that query for some segments of the given array. Everything is up to 100,000. So what this actually means is that all the numbers are pairwise coprime. Like the least common multiple is not greater than the product. Obviously, the product of all numbers is the multiple of all of them, and it should be like the least common multiple. So it cannot happen that some lower number is a common multiple, and if for any two of the numbers in the segment, the LCM is lower than their product, then obviously the LCM on whole segment is lower than the product on whole segment, and that basically means that GCD of any two numbers should be 1, because LCM is the product divided by GCD. We want LCM to be equal to the product, then GCD should be 1. And it is necessary, but it is also sufficient. Basically, we can see that for each prime, it only appears in one of the numbers, and both in LCM and in product of these numbers, the power of this prime will be the same as in the number it appears in. So yeah. So if we wanted to just solve it once, then we could start at the beginning and go left to right, maintain current segment, look at mark the prime numbers that we already had, and if new number have some prime numbers that we already had, then we should stop the segment before it and then start the new one. Right. When we want to do it for multiple queries at once, what will happen kind of doesn't depend on query. Let's say we stay here, then there is a segment that we will eat up, we will go left to right, and then we can't add this element, so the segment ends here. And for each left border, we can try to find this segment, and then to answer the query, we will stay in left border and then make these jumps until we jump out of the segment. The number of jumps is the answer. So the problem is split into parts. Find jumps and quickly calculate the number of jumps for each query. So to find jumps, we will make 2 pointers. Well, if we have 2 left borders, then like on this segment there are more primes than on this one, so it can be that this segment which starts to the right will end before this one. So we will move 2 pointers, like left and right border, which is okay now. And when we like for given left border, we will try to move right border. We'll mark the primes that we have with this new number, and if one of the primes or more were already marked, then like we should stop and then move left border until everything will be fine again, so each prime is used at most once. So we will have this counter array for each prime. How many times have we encountered it? Basically it will be always 0, 1 or 2. We want like on a good segment it only zeros or ones, and we will also have a variable where we store how many bad primes there are, which like we have encountered more than once. Until there are no bad primes, we move right border. When there are bad primes, we know that the previous right border was the last right border for this left border, and we move left border until there are no bad primes. So all of that is done in of n, because we just move 2 pointers, and for each pointer we move, we have to mark or unmark like 2 plus 1 or minus 1 in the primes that we have, which we do in logarithm time. We'll pre-calculate the sieve, and then in this time we can find all the primes the number have. And to quickly calculate the number of jumps for a query, like we start in some left border, want to jump here, we will calculate like binary jumps. So basically what will happen if we make 1 jump, 2 jumps from this point, 4 jumps, 8, and so on, like for any power of 2. And when we want to calculate the number of jumps to get to the right of this point, we will iterate through powers of 2 in the decreasing order, and when we can make the jump such that we still remain in the segment, we will make it and add 2 to the power of k to the answer, and then in the end we will be just 1 jump away from finishing it all. So that one query will work in logarithm time, and precalculation also works in logarithm time, because like to get what is where we will get if we make 2 to the power of k jumps, we will make 2 to the power of k minus 1 jumps from here, and then from the where we have arrived, we will make the same number of jumps, 2 to the power of k minus 1, and in total we have made 2 to the power of k jumps. The problems in this round are boring up until now. So first precalculate the sieve. For each number, I want to precalculate its minimum prime divisor. Now 2 pointers. So until we have reached the end and there are no bad primes, we want to add 1 to the counters of all primes in this number and then move the pointer. If we still don't have bad numbers, then we reach the end and the segment is still good, so it just ends, so we can jump to the end. Otherwise it's -1 and remove the primes that in the left border, because we will increase it by 1 now. So now just calculate jumps. To make it easier, we will say that jump from n0 is n. So when we reach the end, we just jump there indefinitely. And now answer curves. And we need to write the function add. We have to find all the prime divisors and for each of them add this value and maintain the value bed. So the next prime is the smallest prime divisor of x, which is precalculated, while it's divisible by it divide. So we erase all the occurrences, and now if number of occurrences of this prime was at least 2, then we decrease value of bed, because like before we increased for that, now we change it, and if it is at least 2 now, then we increase. And that's it. Okay, the last chance of this round to make an interesting problem. Okay, in problem E, we have to calculate the number of permutations that can be reached from the unit permutation in exactly J operations, in exactly J swaps, basically. For each possible J between 1 and K is up to 200 and is pretty big. Well, what can we say about that? Each swap changes the parity of permutation, so the parity of permutation should be the same as parity of J. If we look at some permutation, can we understand the minimum number of swaps needed to get to it? Yes, we can. Basically, each permutation is a collection of cycles. If, like, for each element we will draw an arrow to the element that written on this position, then we will get some number of cycles, and I state that the minimum number of swaps is n minus number of cycles. Why is that? Because in each swap we can either merge two cycles or unmerge two cycles, basically take one cycle and create two cycles out of them. In the unit permutation, there are n cycles, so if we have some number of cycles, then we can either increase or decrease it by 1. We want to get to the n, so we need at least n minus number of cycles swaps. Okay, so ans for J is ans for J minus 2 plus number of permutations with exactly n minus J cycles. So if we know how to calculate that, we are done. We just need to calculate that for all J from 1 to K, and that's it. How do we calculate the number of permutations with exactly, I'll say n minus K cycles, because K is easier to write than J. We can't have very long cycles, right? So the total length of all cycles is n. We have n minus k of them. N is big, but k is small. So all the cycles are small. So we can try to calculate, like, let's call this thing with n minus k cycles p of nk. We can try to calculate a of nk, the same thing n minus k cycles, but there are no cycles of length 1. why is it better? Because, well, now n is bounded by 2k, because otherwise there will be cycles of length 1, and this thing is easy to calculate using this. Like, if we want the number of permutations of length n with exactly n minus k cycles, then just try what will be the number of cycles with length more than 1. Let's say from 0 to, well, n minus k, because like we have to have n minus k cycles. In each of them there is at least one element, so if we have I cycles with at least 2 elements, then the number of elements is at least n minus k plus I, which should be n, so I is at most n minus k. So all other wait, it should be k here, right? The idea is that it's small. N minus k plus I, which is should be equal to n, so I should be at most k, right? N minus k minus I other cycles will be of length 1, so it's just fixed points in permutations. So the total length of all these I cycles should be n, which is total number of elements, minus the number of fixed points, which is n minus k minus I. So it's k plus I. So we can choose which of n positions will be fixed points. So make fixed points there, and on all the different positions make a permutation with exactly like this number of cycles, but with no cycles of length 1. So in these terms there are k plus I elements, and there should be I cycles, so this is still k, I guess. Okay, so this we can calculate in k plus I time, just, well, basically by definition, k plus I is small. And that's n cube solution, but well, I have not tell you how to calculate this yet, but this should be some pretty obvious dynamic programming. Or at least like it's easy to calculate from this with some inclusion exclusion. But yeah, it will be n cube then, either way. Well, okay, then it's n cube. Whatever. So the plan is to calculate this, which can be done with, for example, dynamic programming. We will go left to right, and basically we will build a permutation as a collection of cycles, and we can each new element we can either insert in some cycle on some position, or make a new cycle. But we have to care about whether there are cycles of length 1, so we will explicitly maintain the number of cycles of length 1 up to this point. So it's dp like we have gone through n elements. There are k cycles now, and let's call it c cycles, and c1 cycles of length 1. So when we have new element, we either create new cycle, it will be cycle of length 1, or we choose some cycle of length 1 and put our element there. There is one possibility. Or we can choose some other cycle and put our element there. It's important where we put it, but basically we can put it after any element, and the total number of element in like kind of big cycles is n minus c1, because we have gone through n elements and c1 of them in cycles of length 1. So there are a constant number of transitions. So we can calculate this dp in cubic time. Then we have basically calculated this thing, and now calculate this with this formula. For that we have to calculate binomial coefficients, but like with fixed n, and like n minus this thing being just up to 2k. We can calculate all of them in of k time, basically. I guess I have to divide modular, but I can pre-calculate small things to divide by. So I can pre-calculate all of that in linear time, and then calculate this in quadratic time, like each of them in linear time, basically. How to optimize this to something faster than n cube? Well, k cube. I'm not sure right now. I think it should be possible, but well, let's solve the problem that is given, for which k cube is enough for sure. I don't want to have n cube memory. I guess I can be okay with it. Like, it's just 400 times 200 times 200. That's not a lot, but I don't want to. So like I want to not store only 2 layers by this, but then I need to calculate these things like after I calculate the dp for them. Okay, basically all the solution is done independently of n and k. So 0, 0, 0 is 1. So when I have 0 elements, I don't have anything. And let's say that a of 0, 0 is also 1. So there is one permutation with no elements and no cycles. There I wrote that k is like we have n minus k cycles, but it's easier to think that it's just the second parameter is the number of cycles. So now iterate over n. Clear the DP. Number of cycles is up to n. Number of cycles of length 1 is also up to n. I can also limit it by big N over 2 because I have to decrease it to 0, but it's not important. So from dp0 c1 I have 3 transitions. Either make new cycle, which will be of length 1. The number of cycles is also increased, right? Choose one of the cycles of length 1 and put the new element there. So its number will decrease. I have to check that there is at least one. There is C1 of them. I can choose anyone. So there are C1 ways to do that. And if there is at least one cycle, well, it doesn't matter here. I can also put it in one of the existing cycles of length at least 1. And there are n minus c1 ways to do that. Copy all of that to the previous layer and put it here. So there's a number of cycles which is at most like n plus 1, but actually smaller than that. In a n plus 1 k, let's do it before the transitions. Then I don't have to do this. A n k is dp0 k cycles and none of them are of length 1. So that's it. I have this. Now I have to pre-calculate the binomial coefficients. They depend on n. Okay, I will pre-calculate the inverses. I don't know why I call them reverses. That doesn't make any sense. I'm just bad at English. So choose n0 is 1, no matter what. Choose n x is choose n x minus 1, but multiply by n minus x plus 1, but divide by x. It's okay that n can be small because like I will traverse x equal to n, then it will be 0, and then everything will be 0 even if it's negative. Like this thing will be calculated somehow, but this is already 0, so it's fine. And now so I want to have alright, I should also maintain like answers for positives and for odd and even. The one for even, because in 0 operations I can get to the initial permutation. So now I want to have exactly this number of cycles. And well, I just try like not this number of cycles, n minus this number of cycles. I try what will be the number of elements that lie in the cycles of length. Oh no, not that. The number of elements that lie in the cycles of length at least 1. Yeah, what did it say here? The number of cycles of length more than 1. So let's do that. There will be at most I of them. And then the number of elements that lie in them is I plus m. So the answer should be increased by we have to choose this I plus m elements, and on these elements construct permutation with with m cycles of length more than 1. And then if I is odd, then increase the answer for odd by uns and print it. Otherwise increase the answer for even by uns and then print it. I guess spaces, right? some more interesting tests will be appreciated, but okay. Yeah, that was not the best round I participated in. And the last problem is kind of fine, but I would not be surprised if it's not fresh, like it was used somewhere before. First four problems are just boring. Not a nice round overall. Thanks for watching.